This is the second part of the Gauss's law lecture, and what we'll do here is a number of examples, the first of which is actually an example we've done already, the electric field of a point charge. We need to revisit that because we're going to learn how to do a Gauss's law example without any reference to our prior knowledge about Coulomb's law or the direction of electric field due to a positive or a negative point charge. All of that information is contained within Gauss's law, as long as you also have an additional piece, which is some logical argument called a symmetry argument. So we're going to introduce symmetry arguments again. We talked about them briefly back when we talked about the electric field of continuous charge distributions. And if you didn't see that, you might want to go back and remind yourself based on that presentation. So we'll talk about symmetry arguments first. We'll do the electric field of a point charge, and then we'll do two more examples. One is the electric field of a uniformly charged sphere, so no longer a point charge, but still a spherically symmetric object, and then a long rod. Okay. So first, symmetry arguments. We introduced symmetry arguments before, and the idea of symmetry arguments is to sort of simplify your life by understanding what the electric field must look like based on the symmetry of the object, of the charged object. And as I mentioned, you should take a look back at where this was introduced in the electric field of a continuous distribution of charge. That was part 2, and I think it starts at 2 minutes 27 seconds. There's a link to it in the description of the YouTube video. For Gauss's law, we're going to use symmetry arguments, and we're going to use them basically every time. And in fact, we're going to use them before we even write down Gauss's law, because Gauss's law is effectively a method of determining the magnitude of the electric field at every point in space. But it doesn't really tell us anything about the direction of the electric field. So we're going to do some qualitative arguments prior to the application of Gauss's law, and those qualitative arguments must tell us what the electric field looks like everywhere. So basically the direction of the electric field at every point in space. And that's what symmetry arguments will give us. A symmetry argument, if you remember from that previous lecture, has 3 parts. You first identify a symmetry of the charged object. So all of these problems will be find the electric field of a bar, of a line, of a sphere, of a hollow sphere, of a disk, something like that. And in each case, you want to figure out what the symmetry of the object is, without any reference to the electric field. A symmetry means that you can do a transformation, so for example, a rotation of the object or a reflection about some plane, and that transformation leaves the object unchanged. And we'll do an example of it in just a second. Then you state that if the object has that symmetry, then the electric field it produces must have exactly the same symmetry. And the reason for that is, if it didn't, then the transformation of the object would leave it completely unchanged, but that would lead to a different electric field. So the same object leads to 2 different electric fields, and that's impossible. And then finally, this is sort of the hardest part, is you have to show that the symmetry of the electric field implies something about the electric field, either its components or its direction, or the relationship between field vectors at different points in space. So usually what we'll find is that there are some constraints on the components. So one example is that, for example, the radial component of the electric field is the only one that can exist, the only one that can be non-zero. Or we'll find some relationships between electric field values at different points in space, like the electric field magnitudes are the same at every point on a circle. So let's see what that looks like in an example, and we'll deal with the point charge again. So if we have a point charge here, there's a number of symmetries that you can find regarding that point charge because it's just one point in space. And one of those symmetries is rotational symmetry. So remember, a rotational symmetry depends on an axis. So I could draw an axis through this charge, let's call it a z-axis, and I can imagine rotating about that axis. So basically I rotate the charge and the whole of space along with it, and no matter which angle I rotate about, so let's say there's some angle that I'm going to rotate it about, the charge will remain unchanged because it's just a point in space. Of course, if I put the axis off to the side somewhere, then the charge might move, and that wouldn't be a symmetry. But as long as I draw an axis that goes through the charge, then the charge will not be changed at all. So this is a symmetry of the charge. That's part A. I've identified the symmetry of the charge. Now I state, well, the electric field must have exactly the same symmetry. So what that means is a couple of things. One is, if I had an electric field, for example, a vector at this point, and I assumed that it pointed in this direction, well, under that transformation, under that rotation, that electric field vector would start to rotate about this axis, and it would change direction. And that cannot be true. So it must mean that this particular choice of electric field is forbidden, and the only kind of electric field that you can have for points that lie on that axis are ones that lie along the axis, so are ones that point along the axis. So this particular electric field is okay. That's one thing that you can find. The other is, notice when I do that rotation will take points on a circle to other points on a circle. So maybe it's going to take us through an angle like this. So it's going to rotate through this angle here. And the field vector that sits at this point will then be rotated so that it sits at this point. What that means for the symmetry is, if the electric field in general cannot change, it means that the electric field vectors at those 2 points must always look like this. So their magnitudes must be exactly the same. In fact, the magnitude of the electric field at every point on that circle must be the same, because they're simply translated into each other by that rotation. And their directions must maintain whatever that angle is with respect to the circle as they go around. So the symmetry argument now tells us those pieces of information. So let's try and summarize. We see that at this point in space here, the electric field can only point radially outward or radially inward. It can't have any components off of this axis. But I picked an arbitrary z-axis here to go through the point. I could have picked it at this point as well, going through this thing. So we know that at any point in space, the vectors must only point away or towards the charged particle. So let's summarize those results. We see that the E vector points toward or away from Q. That comes from the symmetry. And then we saw that the magnitudes of E must be the same at every point on this circle, but you can imagine that if I allow that z-axis to change to a different direction, then that will connect this point to a different circle. And in fact, what that means is that every point at a certain distance from the charge must have exactly the same magnitude of the electric field. So the magnitude of E at a distance r from Q is the same. Is the same at all points on that sphere. So you can imagine that there's an enclosing sphere around this point charge, and at all points on that sphere of radius r, the electric field magnitude is the same. And then using our first result, each of those electric field vectors will either point away or towards the charge. So, as I mentioned up front, we need to use a symmetry argument so that we understand exactly how the electric field looks before we can even apply Gauss's law, and that's what we've done. Let's apply it to the example. So, we're asked the question, what is the electric field of a point charge? And I'm just going to go through it very quickly, summarizing what we found. We know that our qualitative argument, so using symmetry, seems I've forgotten how to spell it. Using symmetry, we know that E points away or toward the charge at every point in space, and magnitude of E is the same on a surrounding sphere about Q. So we know basically how the electric field looks, and I'm not going to draw it here, but it's basically what we have been drawing for the field lines of an electric charge. So that's our qualitative argument. Now we make the quantitative argument, which is that we apply Gauss's law. And sometimes we'll have to do that multiple times in order to find the magnitude of the electric field at different points in space. But in this case, we really only need to do it once because this charge distribution is so simple. So the steps of applying Gauss's law are, well, first we might write down Gauss's law because it tells us something about what we should do. So I'll write it down. It's the area integral over a closed surface, that's why I draw that little circle in the integral, of the electric fields dotted together with the area vector, but remember that means dotted together with the normal vector at a point in space, and then you integrate that over the area. So you look at the dot product of the electric field with the normal vector at a point on the surface, you multiply that by the area chunk, and you add them all up. That's called the flux of the electric field through that surface. And then the other side of the Gauss's law says Q enclosed by S over epsilon naught. So we wrote down Gauss's law, and now it's reminded us exactly what we need to do. First of all, we need a surface. So we choose a surface. And now, last time I just chose the surface, I told you we're going to choose a sphere that's centered on Q. But now we know why we're going to choose that sphere. And the reason is that symmetry has told us that E points away from the charge at every point, and that on a surrounding sphere about Q, the magnitude is the same. So if we choose our Gaussian surface to be that surrounding sphere, so here's our S, then we know that at any point on that surface, we will find exactly the same magnitude of E. Now let's assume that our charge is positive, and we'll draw the electric field at a point on the surface. So I'm going to draw it pointing away from the charge, but I'm actually going to show that it must point away. And then I draw, remember, the normal vector at that point as well. And we might do that for a couple points. So let's have it point away. Remember, it has to either point away or towards. That's what we found from symmetry. And here's our normal vector at this point. And then we'll do one more. Here's E pointing away. And we do the normal vector pointing away as well because it's perpendicular to the surface at that point. So looking at those points, I can write down the integrand here. We see that E dot n at every single one of these points is simply going to be equal to the magnitude of E. And that's because the magnitude of n, it being a unit vector, is 1, and the angle between the two vectors is 0, so that also gives us 1. So we end up with that. The Q enclosed by the surface, well, that's just Q, so I can write Q. And then we have epsilon naught here. Then we actually apply one of the things we learned from symmetry. So because the electric field magnitude is the same at every point, we see that E magnitude must be a constant, and therefore we can pull it out of this integral. So we get E magnitude as a constant. We get this integral over the surface of just adding up the areas equal to Q over epsilon naught. And as we found before, this just means adding up the area. So we get 1 over 4 pi epsilon naught Q over r squared, because the area of a sphere is just 4 pi r squared. One little point, remember our symmetry only told us that E points away or towards, and I chose it to point away, and it turns out that that was the right choice because I found that the magnitude of a vector is a positive number. Q is positive. Now if either I had assumed Q was negative and drawn the same picture, or if I had assumed that E was pointing in and gotten a negative number when I took the dot product, then I would have gotten magnitude is equal to a negative number, and that would have been the wrong choice. So I would have just said, oh, E was pointing in the wrong direction. It must go the other way. So you see that now we have symmetry and Gauss's law providing every detail of understanding what both the direction and the magnitude of the electric field from a point charge is. Now let's do some more complicated examples. Find the electric field of a uniformly charged ball of radius r and of total charge q. So let's draw that. So now we don't have a point anymore, but we have a whole volume of charge. It's again q. Let's assume that it's positive. And then it has some radius, r. So before we even write down Gauss's law, we have to do a qualitative argument, which is a symmetry argument. It turns out that the symmetry argument here is identical to the one that we did before for the point charge. So let's just quickly review it. If I have a ball and I put an axis through it, like this, then I can rotate about that axis and the ball remains exactly the same. In fact, I can do it for any direction that I want. So let's try and write that down concisely. So rotation about any axis through the center is a symmetry. It's a symmetry of the charge distribution itself. Next step, E must have same rotational symmetry about any axis through the center. And then remember, the third step of the symmetry argument was to state what must be true about the electric field then. So E field must, so 1, point toward, away, from center. So exactly for exactly the same reasons as before, I can look at a point on this axis, and unless the electric field is pointing along that axis, then it will be changed by the rotation. So I know that E must either point towards or away from the center of the ball. And of course that's true for any point in space, because I could draw a different axis that's pointing in a different way, and I could choose the electric field at a different point, and it also must be pointing towards or away from the center of that ball. So that this statement applies to every point in space, that electric field points towards or away from the center of the ball. And then the second statement is also the same as what we found previously, which is that the magnitude of E is the same at all points on any sphere centered on the point. So I can draw any sphere around this object, and that means that I could draw a sphere inside of the object or a sphere outside of the object. And on either of those spheres, the electric field at every point on the sphere will be exactly the same magnitude. So again, our qualitative argument has given us everything that we need to know about the direction, what the electric field looks like. Now we're left to Gauss's law to determine what the magnitude of the electric field is. So Gauss's law. And in this case, we actually need to do Gauss's law twice. And the reason is because it will be a qualitatively different situation doing Gauss's law outside. So here's a sphere that I can draw outside, than it will be for drawing one inside. So maybe I'll just redraw it here. So Gauss's law, do it twice. So let's do it inside first. So for the case of the distance from the center greater than the radius of the ball, we have this picture. And I choose, again, a spherical Gaussian surface. And I choose it to be a spherical Gaussian surface for the same reason I did last time, which is that I know that the electric field has the same value at all points on a sphere. So that's going to allow it to be a constant within the integral and pull it out. It makes our calculation easier. So in this case, we have Gauss's law, integral over that surface, make sure to label that surface, of the electric field dotted with the normal vector at every point, integrated over the area, is equal to Q enclosed over epsilon naught. So we show what we're doing by choosing a point on the surface. I'll choose this point, and I'll assume that the electric field is pointing away. Remember, I could choose it to point towards if I wanted to. And then also at that point, I need to show the normal vector. And just like we saw before, the dot product of those two things will just give me back the magnitude of the electric field. So I have integral over the surface of magnitude E multiplied by 1 for the magnitude of the normal vector, multiplied by 1 for the angle between them, the cosine of the angle between them, dA. And the charge enclosed, well, that is just the total charge. So that's, again, just Q over epsilon naught, because the entire ball is enclosed by my chosen imaginary Gaussian surface. Okay, then I can continue, and at this point I can use what I found by symmetry. I can pull the electric field outside of that integral, and I'm only allowed to do that because I know that the electric field magnitude is the same at all points on the sphere. So at all points on that surface area, the value of magnitude E is the same. And again, my calculation of the integral could hardly be called a calculation. It's just adding up the area of a sphere, which I know to be 4 pi r squared. And I should label that sphere because I've introduced a different distance here. In my chosen Gaussian surface, I've introduced a radius for the surface itself. And I chose it to be that r, which is just some value outside of the ball. And finally, I find that the electric field magnitude outside of the ball is equal to 1 over 4 pi epsilon naught Q over r squared. So that is the electric field of a ball, but outside of the ball. And interestingly, it's exactly the same as if all of the charge in that ball were simply located at a point charge in the center of the ball. That's our first case. Now we need to do a second case, and that is for r less than capital R. So for r less than capital R, we need to draw a different picture. Maybe I'll make it bigger. So I've zoomed in the picture, And now I'm looking at, again, a circular Gaussian surface, but I'm going to place it inside of my ball. So I have r less than the radius of the ball. And we just go through and do Gauss's law again, exactly the same way. So I'll write down Gauss's law, the integral over the surface that I've chosen. Again, I should label it, of the electric field dotted with a normal vector on the surface, multiplied by the area element, and that's equal to the Q enclosed over epsilon naught. Notice that I don't skip any steps. I write the whole Gauss's law out again. And then in order to evaluate this integral, I need to draw those normal vectors. So let me draw one. I'll draw the normal vector at the surface, and I'll also draw the electric field at that point. And I'll just assume that it points outward. And again, the dot product of these just gives me back the magnitude. So that is magnitude of E. A magnitude of n is 1, cosine of 0 is 1, dA. And now comes the slightly different part. Gauss's law tells me that I need to find the charge enclosed by the surface that I've chosen. Remember, it's my business. I choose the surface myself. But now that I've done so, I need to know what the charge is inside of that surface. So that's just a little bit complicated because I need to figure out how much charge is inside of the total ball. Well, the amount inside of the ball is going to be given by the ratio of the volume of that ball to the volume of the whole thing, multiplied by the total charge. So let's write that out. So we have 1 over epsilon naught, and then it's going to be 4/3 pi r cubed over 4/3 pi capital R cubed. So that's the ratio of the volumes of the Gaussian region inside of the surface to the total region. You notice that as the Gaussian surface gets closer and closer to the total radius of capital R, then this becomes 1. But I'm interested in the case where it's smaller, so we have a ratio there. And then you have to, of course, multiply that by the total charge. So that's the fraction of the charge that is enclosed by the ball. Okay, the rest of it is fairly simple. Again, because my symmetry argument told me that the electric field is the same at every point on that surrounding sphere, I can pull it out. So again, my integral becomes very simple. Of course, all of this stuff cancels out, so I get q r cubed over capital R cubed, with an epsilon naught still there. Let me give myself just a little more space. And then I have the electric field magnitude is going to be, remember, this integral is 4 pi r squared, little r squared, because it's just the area of this surface. So I'm going to have q r cubed over epsilon naught r cubed times 1 over 4 pi r squared. Leaving me with 1 over 4 pi epsilon naught, that's k, q r over r cubed. That is the expression for the electric field of a ball, but for points inside of the ball itself, as long as it's uniformly charged. So it's interesting. You see that the electric field outside of the ball, well, it looks just like that of a point charge, but the electric field inside of a ball is actually increasing linearly with the distance from the center. So we might even draw what that looks like on a graph. I'll just do it off to the side here. So if we wanted to graph the value of E as a function of R, and let's place capital R somewhere there. Well, the value of E, so this is the magnitude of E, it's going to be increasing linearly from 0 until you get to capital R, and then it's going to be dropping off as 1 over R squared. So the magnitude of the electric field looks like that. Final example. Find the electric field of a long, thin rod with linear charge density lambda greater than 0. So in order to do this with Gauss's law, we really need to assume that the rod is infinitely long, because only if it's infinitely long will it have the symmetries that we need. So I'm going to draw it as such. I'm going to draw it as a thin rod that just sort of goes on forever. And now I want to find the electric field due to the rod, but as we know, we need to make some qualitative arguments first. In order to find out what the electric field looks like at every point. So let's look at a couple, well, first let's determine what some symmetries of this rod are. So one symmetry is a reflective symmetry. So rod is symmetric about reflections through a perpendicular plane. So that's our first statement for our first symmetry, meaning if I draw a plane here, then I can reflect the rod, and the rod will be the same. Because it's infinitely long, so there's just as much length on either side, it will look exactly the same. Okay, if that's true, so E has same symmetry. And then finally, what does that imply about E? Well, notice that for particular points, if I choose a point in the plane that I'm doing the reflection, and I look at the electric field vector which has its tail there, the electric field at that point, then, for example, an electric field that points like this would not be allowed. And the reason is because if I do that reflection, then the electric field vector would flip. It would go point in the opposite direction. And then we'd have two different electric field vectors at the same point for the same object, and that's impossible. So this reflection implies that E must point in the plane. So that leaves a couple of options. It leaves the possibility that the electric field is pointing sort of circumferentially around this thing. That would still be in the plane. Or it is pointing away from the plane. And it turns out that it can only point away from the plane. And the reason for that is, it can only point away from the rod. And the reason for that is because you could do another reflection where you put the plane like this, and then any electric field which pointed circumferentially, so in this point here, any field lines that point into or out of the page, those would be impossible because a reflection would change their direction. So it turns out that E points away or toward the rod. So that's our statement about the direction of the electric fields. We need to make one more symmetry argument, so let's call this symmetry argument 1, and then we'll make a symmetry argument 2, and that is that the rod is symmetric about rotations any angle about, we'll call it the z-axis. So I'm talking about this axis here that points, well, it's called its axis of symmetry. So any rotation about this axis will not change the rod at all. And that means it's a symmetry. And so if that's true, then that means the electric field, E, also rotationally symmetric. And what does that imply about the electric field? Well, remember that a rotation will connect points in a circle. So the points here must have exactly the same magnitude of the electric field, because you can rotate one into the other by an arbitrary rotation there, and the electric field must stay the same. So the statement about the electric field is that the magnitude of E is the same on any circle about the rod. So let's just finish up the problem now. We can do the quantitative part. We start that with writing down Gauss's law. So let's write it down. And let's draw ourselves a picture. And as Gauss's law tells us, we need to choose a Gaussian surface to use. So in this case, we need to choose a Gaussian surface which allows us to use the rules we found about the electric field. So one of them was that the electric field is the same on any circle. So we hoped that we could use something that has that circle so that in the end the electric field will be the same at every point on that surface, and you can pull it out. We know that the electric field must point away from the rod, so we might like to have a surface in which the electric field is perpendicular to the surface, so this E dot n is very simple. So using those two ideas, the Gaussian surface that we choose is a circle around the rod and then a flat piece. So we choose a cylinder. This is solid. And this will be our surface. So we choose a cylinder of a certain radius. And let's do Gauss's law now, and we'll see why that is a good choice. So, so far we've just said that we can do Gauss's law and we can talk about this area integral as just a single integral. And that's because every piece of the sphere that we used before was sort of identical in this integral. There was nothing different about E dot n at any point on the sphere. But as you can see here, the electric field at these regions is going to be different than the electric field at these regions here on my surface. And remember, we have to use the closed surface. So when we draw the cylinder, we mean the entire soup can here, including its curved sides, but also its top and bottom of the can. So I think it'll help if we show the electric field at a few places. So we know that the electric field points away from the rod, and at that point the normal vector is perpendicular to the surface. So that's one little calculation for the integrand. But if we look at a point over on the side, at this point, we know again that the electric field points away from the rod, but the normal vector is going to be perpendicular to surface looking like this. So that's a different calculation. And similarly, over here, we have an electric field pointing away from the rod, but a normal vector pointing perpendicular to the surface. And maybe just one more down below, we see that the electric field is pointing away from the rod, the normal vector points away from the surface. So you can see that there are three sides. So let's break up Gauss's law into three sides. So it's going to be the integral over, let's call it surface left of E dot n dA plus the integral of surface right of E dot n dA plus the integral of surface curved, meaning the sides of the soup can, of E dot n dA, and that's Q enclosed over epsilon naught. So now we can do each separately. And of course I can do this. I can separate an integral into a sum because an integral is just a sum, as we've seen. So you can always just separate it into those parts. So let's look at the left side first. So on the left side we have E dot n looking like this. The dot product of those two vectors, because the angle between them is 90, is just 0. So we find that this term just becomes 0. Every term within that integral is going to be 0, and therefore the whole thing goes to 0. The same can be said about the right-hand side. These things have a dot product of 0, so we say E dot n there is equal to 0. We might give ourselves a little note, E perpendicular to n at those points. And we're left with just the curved surface here. And you can see that the one that I drew here and the one that I drew here are basically identical. E dot n is just the magnitude of E. So in our next line, we can write that the integral over the curved, oh shoot, I drew that wrong there, I'm sorry. So the curved surface is the one that is left, and these both are 0 because they were the left and the right ends. The curved surface is just going to turn out to have an integrand of magnitude E, dA, and then we have Q enclosed, and let's deal with Q enclosed now. So I specified the radius of this cylinder, but I forgot to specify the length of the cylinder that I've chosen. We'll just call it L. And the reason I need to specify that is because now if you look at the ends of this cylinder, it's bounding a chunk of the infinite rod. And that chunk has length L. And we were told that the density of this rod is lambda, so the Q inside is going to be equal to L times lambda. That's just the amount of charge which sits inside of the cylinder that I've chosen. So I can write over here that Q enclosed is just L times lambda, and we still have the over epsilon naught. Now we get to the step where we can use the rule that we found about E being the same on any circle. So I have this integral on the curved surface, but we know that E is the same on any circle. So that means that these E's are exactly the same magnitude, which means that I can pull them out. So I get E S curved A is equal to L lambda over epsilon naught. Sorry, dA. And finally we do the integral, and as usual, doing the integral is nothing hard. It's just the total area of that thing you're talking about. Now remember, we dropped the circle up here, because we took the entire surface of the soup can and split it into 3 parts, and we were left with only one of those parts, which is just the sides of the soup can. And the sides of the soup can is actually a rectangle, right? If you like cut here and then open it up, then you see that that's actually a rectangle. And it's a rectangle with a length L and a side of this circumference. So we can write the area there as L times 2 pi r. And we're almost done. We find that the magnitude of the electric field, the L's will cancel here, is equal to lambda, let's say lambda over 2 pi epsilon naught r. And remember, 1 over 4 pi epsilon naught is equal to k, so you could also write that as 2k over r.